Hello, my name is Ivan Ruchkin. I'm a PhD student at Carnegie Mellon University. I'm going to talk about the basics of an architectural approach to heterogeneous modeling and verification of cyber-physical systems. It is an NSF-sponsored project between Carnegie Mellon and Toyota. I'm only going to give you the intuition about it without diving into the technical detail. Okay, so imagine you need to create a cyber-physical system, or CPS, a smart intersection. The system would be installed at every vehicle, and it would help vehicles drive through the intersection automatically and safely. The least you would want to do to create it is to write the source code in something like C or Java that would tell vehicles what to do and when. But this is by far not enough to create a modern and safe cyber-physical system. You would need to do a fair amount of modeling as well. For example, you could create a software model that would check if your software has any concurrency bugs, such as deadlocks or race conditions. You could use state machines or process algebras for that purpose. Then you might want to create a control model in order to refine your controller to make sure that cars drive smoothly and appropriately at all moments. You might want to create a physical model using, for example, Modelica, to study closer the forces that act on a car and the physical characteristics such as braking or turning. You might create a hybrid model using, for example, Chimera, to make sure that the continuous behaviors of your system play well with the discrete decisions of your software. All these models are known to be heterogeneous because they are created using very different formalisms and describe potentially different parts of the system at varying levels of abstraction. Despite all the differences, they are all very useful to address varying aspects of the CPS design. However, their differences make a lot of room for inconsistencies in between models. For example, how do you know that your hybrid model respects all the decisions made in the software model? Or how do you know that your control model behaves appropriately according to the characteristics of braking that are defined in the physical model? These issues, if not found at the right moment, may result into critical failures of your system. Another challenging aspect of CPS work is verification. That is, how do you take all the models and the information in them and prove that your system is safe? Here's our solution. We call it an architectural approach to cyber-physical systems. We take all the models and we create an architectural view for each of them. An architectural view is an architectural high-level model created in a flexible and rich formalism of an architecture description language. We use Acme for this project. Each view highlights the important aspects of the model and abstracts out the details that are not important to other models. Now that we have the views, we can establish relationships or mappings between them and check for consistency of the underlying models. Or we can even create more views and relate the existing ones to them in order to simplify verification. For example, you could take your braking times from this model and propagate it to this level in order to prove that your system adheres to the safety specification. This is a very powerful approach of dealing with heterogeneous models that does not mean that you have to necessarily dump one of them or any of them, and you do not have to model your system in one single formalism, which would probably be very inefficient. During our project, we did a number of case studies. One of them, Star-Mac Quadrotor, had a goal of checking the consistency of the models describing this quadrotor. Another one, CCAS Stop Sign Assist, had an objective of verifying the safety of an algorithm that told the car whether it's safe or not to move through the stop sign. Our current project, Robot Collision Avoidance, has a goal of designing and verifying the controller for a moving robot so that it can safely avoid the obstacles. This is it. Thanks for listening. If you want to find out more about our project or many other projects about CPS, you could go to cps-vo.org. This is it. Thank you. Bye.